Hi everyone, this is STAT512 Group 4. Um, Here in the final project, we are trying to understand the determinants of life expectancy. First, must know that understanding what affects this is an extremely complex task. So we are here to investigate how these different factors can potentially affect life expectancy and how they can relate to each other. Our research is divided into four key areas. First will be vaccination rates and location. Second will be lifestyle and education. The third will be the economic indicators, and the last will be mortality rates. First, we are studying about the relationship between vaccination rates and life expectancy and how they vary between the eastern and western hemispheres. In our initial model, we include the vaccination rates for the four major diseases, the categorical variable hemisphere, and the interaction between hemisphere and each of the vaccination rates. The model summary on the right shows that these predictors collectively explains the variation in Y as shown by the very small p-value, but we'll need to do some further diagnostic on it. The residual plot shows that there is a downward linear pattern in the residuals. This is again confirmed in the QQ plot to the right, where um, the errors they alternate below and above the linear line, suggesting there may be a trend to the errors. To confirm this, we do a normality test and the test for constant variance, which both of them rejects the null hypothesis and suggests that the residuals are not normally distributed, as well as they have constant variance. To mitigate on this, we first try to do a Box-Cox procedure. However, Box-Cox shows the highest lambda. We allowed it to be an optimal lambda, which means that the log likelihood function does not converge to a right value. This shows that the Box-Cox may not work as expected. Um, Secondly, we try a log transformation on Y, which, shown by the QQ plot, does not fully fix the issues of non-constant variance, but it will mitigate the issue of the skewness of the data, since the log transformation can compress large values. Um, to select the model, we do a model selection, the best subset algorithms, which across 7 metrics, it used 4 best models. To further confirm on this, we do a k-fold cross-validation across 4 models, which suggests model 3 has the best performance across mean square error, R-squared, and mean average errors, while model 1 offers much more stability since it has the smallest standard deviations among these 3 metrics. However, once we account the fact that the performance across all 4 models are marginally different, while model 1 offers a lot of stability, we will use model 1. In addition, we also do check for influential points, which suggests that there are 150 influential points all over 2,800 observations. Also, the VIF demonstrate that there is an issue of multicollinearity between diphtheria and polio. To mitigate this issue, we decided to use a robust regression and weighted least squares combination on the log transformation of Y. From then on, we test on the hypothesis if there is a significant interaction between measles and hemisphere, since it is the only interaction term left after model selection. We apply bootstrapping to find the confidence interval of this coefficient. Since the interval does not include 0, we can say that the interaction is significantly different from zero. However, given that the interval is so small and the existing assumptions violations, we must understand this interpretation with caution before making any causal relationship.
We want to determine if the average amount of years spent in formal education has a marginal effect in the prediction of life expectancy. The response variable is life expectancy, and there are 5 continuous predictor variables: alcohol consumption, BMI, incidence HIV, adult mortality, and schooling. Since we want to determine if schooling has the marginal effect, we'll perform a GLT test on this predictor's beta. However, before we can perform this hypothesis test, we have to go through a model diagnostic process. We determined that our initial full model has issues of non-constant variance and non-normality, as seen in the residual plot and normal QQ plot respectively. With the Bruce-Pagan test, it has a p-value less than alpha equal to 0.05, meaning it rejects the null hypothesis that the variances are constant. The Shapiro test also has a p-value less than alpha equal to 0.05, indicating it rejects the null hypothesis that the errors follow a normal distribution. We try to remedy these issues by performing a Box-Cox transformation on the model, where we obtain a lambda value equal roughly to 1.24. However, after performing the Shapiro test and BP test again, we still obtain p-values that are less than alpha equal to 0.05, indicating that we reject the null hypothesis and our issues of non-normality and non-constant variance are present. We try another remedial measure by taking the natural logarithm of life expectancy. When we perform the Shapiro test and BP test again, we still obtain a p-value less than alpha equal to 0.05. Since our issues of non-constant variance and non-normality are still present, this indicates that we'll have to do a more extreme remedial measure, such as weighted least squares. However, when we look at the model summary using natural logarithm of life expectancy, we notice that the residual standard error is extremely small, with a value of 0.0328. This indicates that this model fits well with the data. The best sub-algorithm, stepwise algorithm, and k-fold cross-validation all confirm that the best MLR model to use is the 5 continuous predictor variables with the natural logarithm of life expectancy, as this model produces the lowest values for specific criteria. Continuing the diagnostic process on our new model, multicollinearity does not appear to be an issue, as the variance inflation factors across the 5 predictor variables are all less than 5, with some even being close to 1. The student ties deleted residual shows that there are 4 outliers on Y, and the hat matrix leverage values show that there are 179 outliers on X. With a quick box plot, these outliers on X can most likely be correlated with the predictor adult mortality. The DFFITS, DF betas, and Cook's distance measures show that there are a significant amount of influential points within our model, whether they are on fitted values or regressional coefficients. Since we have issues of non-constant variance and influential points in our model, we apply the remedial measures of weighted least squares and robust regression to obtain our final model. However, when performing the Bruce-Pagan test and Shapiro test again, we still obtain p-values that are less than alpha equal to 0.05. This could be due to the fact that mortality is never uniform and is always unpredictable. We now can perform the hypothesis test. Since we performed the remedial measures of weighted least squares and robust regression on our model, we have to utilize bootstrapping to calculate the 95% bootstrapping confidence interval for the predictor variable schooling. This confidence interval is negative 0.012 to negative 0.011. Since this confidence interval does not contain 0, this indicates that schooling is a significant predictor within our MLR model. Therefore, we can conclude that schooling has a marginal effect on the model predicting life expectancy and should not be dropped.
Hello, my name is Josh. My research question is, how does a country's development status moderate the effects of GDP, population size, and schooling duration on life expectancy? So, to prepare the dataset, I checked for missing data first. Couldn't find any, and so I checked for outliers using box plots and Cook's distance. Also, nothing significant really of note, and the data is ready to go. So here's the beginning of my MLR model. Also, nothing crazy, pretty standard, just figured I should show it. Let's move on though. Next, I checked for multicollinearity within the model. On the left are the results. Economy status and the schooling interaction both exceeded the common VIF threshold of 5. That's a problem. To address the problem, I applied a ridge regression. I then compared the coefficients to my original model, and on the right, you can clearly see that the ridge regression successfully shrunk these values towards 0, thus solving the multicollinearity problem. Moving on to diagnostics, I'm checking for 3 main things here: linearity, normality, and homoscedasticity. To assess my model's validity, I generated 4 diagnostic plots. Both of the plots on the left showcase an uneven spread of residuals on top and variance on bottom. And then turning to the QQ plots on the right, we can also see strong deviations from the ideal diagonal line. Taken together, these diagnostics show that my model suffers from a lot of things: heteroskedasticity, nonlinearity, and non-normality. The Broich-Pagan test and Shapiro-Wilk test also confirm these plots. So to fix these problems, I performed a Box-Cox transformation, and now the model is ready. The model was validated using k-fold cross-validation and bootstrapping with 1,000 instances. What's important here is that 2 of the effects, economic status and the schooling interaction, were strong and clearly different from 0. This means the model reliably captured real patterns in the data. So, after all that prepping, the model is finally ready for hypothesis testing. And my question is, after accounting for socioeconomic and regional factors, does the interaction between schooling duration and economic development status significantly predict life expectancy? The null says that there is no significant interaction, and the alternate hypothesis says that there is. Ultimately, through R analysis, I didn't put the code here because it would be too much. I found that the p-value is far below the alpha of 0.05. Therefore, we reject the null. There's strong evidence that the interaction between schooling duration and economic development status significantly predicts life expectancy.
With that, we hop on to the last research question. Have mortality rates at birth under age 5 and thinness prevalence from ages 5 to 19 affect changes in life expectancy over the years? And have these changes been positive or negative? So with that, we start with the initial model with the 4 variables that I've just mentioned. From here, the code shows inflated t-statistics and also a little bit of a difference in coefficients across the 2 age ranges in thinness prevalence, one being negative and the other being positive. So with that, I hop onto the diagnostics and try to see if there are any problems. Starting with the ANOVA tables, having some inflated death values for the death rates under 5. The BF test and BP test both reject the null hypotheses, showing there is non-constant variance. The Shapiro test same, rejecting the null hypothesis, violating the normal distribution for the data, and the VIF variance inflation factor showing the death rates might have multicollinearity. Those could be visualized in the QQ plot, quanta plot, and the residuals plot. The QQ plot shows a large range of residuals are on the lower side, and for the QQ plot, both ends just don't follow the regress line. There are 2 remedial measures that are proposed, since death rates of age under 5 is always bigger than the infant deaths. I would decide to subtract the latter from the formula just to obtain a little bit of the rate difference. And onto the transformation of y is a Box-Cox procedure. The power factor is found to be about the square root of 2. There is some new model. It shows a small improvement according to the diagnostic test that I've done, except the variance inflation factor, which for both death rates it's lower than 10, lightening the issue of multicollinearity. Then we're here to find the best subset for the final model. Added two variables, the year variable, such that the year 2000 would have the value of 1 all the way to 2015. And then there's another variable, which is the indicator one for a developing country. And then we hop onto the k-fold cross-validation. The red ones are the best ones that should have been used for the decision making, and the green ones are just the additional ones just to check if there are any ones that are the alternatives that are better, and in which the final model was decided to include both the added variables I've just mentioned, and there is the final model. And then we go to hypothesis testing and see if the time of year, meaning the 2000 to 2015, has any linear impact on the life expectancy. So from the ANOVA test, it shows that the null hypothesis is rejected, and such that the time of year has linear impact. And then we undergo a little bit of bootstrapping to find the confidence interval at 95% of the time of year, and it's to be found at 0.0229 to 0.0746. Multiply that by 14, which is the duration between 2000 and 2015, and it could be concluded that there are countries that over the past 14 years might have increased their life expectancy by 1 year. Now, in a discussion. Firstly, the hypothesis test reveals that association between measles vaccination and life expectancy is more pronounced in the Western Hemisphere. Since the model assumptions remain partially violated, it's important that we interpret this result with caution. Secondly, knowing the amount of formal education an individual has is necessary when predicting their life expectancy, and can influence the amount of healthcare they have access to, declining their health in the long run. Furthermore, more years of schooling has been shown to have a greater positive impact on life expectancy in developing countries. Investing in education in developing countries could yield larger gains in population health and longevity. Finally, given the mortality rates and other factors, while life expectancy does not have a strong relation with thinness, it's been steadily increasing over time. Therefore, it should be known with optimism where all factors considered in research questions will gradually improve health for all, and so as to live longer. Thank you.